Vale. Okay, hello everyone. Sorry for the last minute technical issues. Today we welcome our home researcher Juan Betancourt to give a talk about single photon geek in Betelgeuse occultation. Juan has been a PhD student in the United Kingdom and started also a postdoc here in the IEC, where he later on started a position as a titular professor of the Universidad de La Laguna. So we have the pleasure to have one of our own here today.
Well, first of all, I want to explain why I am giving this talk, which is quite unusual for me. And, I have been involved in this work in some technical and some statistical analysis, but in the end, I have got involved. Also, this work can be considered a precursor or a case study for the project La Palma Interferometer, which is a project that tries to take advantage of the synergies between all the telescope of these 7 couples of telescope that we have in El Roque de los Muchachos. And by means of interferometry, we can achieve, there is a potential of 50 micro-arc-second spatial resolution. Well, this is a project for the future, but as I said, this the work that I'm going to describe here is, in a sense, in some aspect, precursor to this one. And it was considered, since this project is important because it aims at taking advantage of these capabilities, and in the future, there is it could be used both the telescope in both observatories in Roque de los Muchachos and Izaña, and it has been considered one of the strategical projects of the ISC. No? And well, it was considered interesting or convenient that I give this talk. No? So I will try, the talk is based on this it's based on this, it's a description basically of this paper that have been submitted to Astronomy and Astrophysics. I will give a summary of the paper, and then we'll switch on to my main contribution to it, where some interesting, from my point of view, statistical consideration that are of general interest for everybody working in astrophysics are contained. Okay. So, well, the aim of this work is been to explore the possibilities of the capabilities of the SPAD technology for astronomy. This is the detector SPAD are single photon avalanche diode, have certain advantages with respect to the classical THEMOS and TTDs, in the fact that that they allow to count photon individual, because of course you can the basic physics of this is very simple. You have an p-type semiconductor and an n-type superconductor. They are polarized in the reverse direction with a high potential, so that that you remove all the electron from here, which are minority conductors, and you have a very strong field in this direction. Well, that accelerate electron in this direction. And when a photon comes and promote an electron the valence band to the conducting band, the field, the field accelerate the electron enough so that when it takes the next collision, it promotes another electron to the conducting band, and so on, and you produce an avalanche. No? And the interesting thing, of course, you can integrate and count the total current, like the CCDs, the total charge that have been deposited. But the important thing, the interesting thing, is that you can count every avalanche individually, and so you can count photon coming. And well, here you see some of them achieve the resolution of 100 picosecond, not the one that we are going to consider we have used in this work, but this is achievable. So that you have 10 to the 10 photogram per second. Well, here, yes, you have an example of how usually in the technologies is how currently they are used. This is the leader using automotion to measure the distance to the other vehicles. I know. Well, you have the leader principle. You have a laser that emit to the target, and you collect here in the you using a SPAC tool. Well, this is just an example, not of much interest. Here is the array that the SPAC that we have actually used in this work. Just to give you some idea of the dimension and characteristic of these arrays, you see it is very, very small. The arrays contain 60. ¿Qué pasó ahora? The array contains 64 times 64 pixels, and the total size is just 1.5 millimeter. This is just 1.5 millimeter times 1.5 millimeter. Here, one of this unit here is here. This is the unit, and all this is the electronic part, and this is a photosensitive part. This is like 25 micrometers, and the area is 21 micrometer squared. No? So really very small. No? And well, here say this challenges and limitations of the actual technology. Well, one of the limitations, let's move to, one of the limitations is the very, as you can see here immediately, is the very small area coverage, because only this small part is photosensitive. Here you have the display, the increase with every and is the unit are placed in this form. They are grouped they are bunched in group of 4. Every one of these is a photosensitive area. No? And you can see visually how small the coverage is of this area, of the whole area of the array. It is just 3.5%. This is a very high limitation. Okay. Well, this is the description of this work in which this technology has been tested in the case of And occultation, and this rock is called Leona. It is an asteroid, and there was an occultation in December 23, little bit over a year ago, and it was used with this telescope, 10-inch telescope, at the observatory of Nerpio in southeastern Spain. No? Well, before going to the detail of this observation, a little bit more about the technical characteristic of this technology. We have we have the 64 times 84 read out asynchronous. It is in fact that means that it doesn't measure at given time, but it is even driving. It give it assign to every event its time. You know? The filling factor 3.5, the site of the unit 24 micrometer, and well, this is the maximum output. It can deal with 40 million events per second. And the time resolution is 3 nanoseconds. The time resolution is 3 nanoseconds, but we are not exploring that much here. All the analysis that we have done are within 1 microsecond. But in the future, for the interferometer, it would be necessary even to go below in nanosecond. Well, this is the trajectory. This here is the observatory of Astrocamp in Nerpio, and from which very close to the center, to the center line of the occultation. No? So, well, you can have here a simulation, and you see that because of the form of the asteroid, is elongated, so it doesn't cover completely it doesn't enter completely within the disk, which is important for. Well, here you have the image, you have the pixel that has been activated. This contains the diffraction pattern. So we have used this only this area here that have something like a number of 78 pixels, effective number of 78 pixels, and this is what have been used to carry out the observation, no? The analysis of the observation. Well, basically what we do is an analysis of the arriving of the sequence of arrival of photons. Huh? Every photon has a time assigned, and we make the statistic of this. Well, most of you know that or think that they are completely independent, and this is Poissonian distribution. That is almost like that, but not quite. But here it is so. The photon themselves arrive almost independently. But so they will follow this distribution, classical Poissonian. Lambda is the mean number of events within the given amount of time. In our case, it would be a microsecond. But there are a couple of effects that make a difference with respect to this, and I will enter in the technical details later. So just to point out that the actual distribution, because of the detection, not because of the photon themselves, follow this distribution with this extra parameter theta, which is, when you drive it to zero, you recover immediately Poisson. In fact, the the effect of the theta comes through theta time the mean number of photon in that time, and it related to a parameter x, which is has to do with the crosstalk, that some pixel, when activated, may falsely activate neighboring pixel. This is called a crosstalk, and it's a very technical effect, but that we shall see that it causes the distribution to depart from Poissonianity, and we take advantage of it to measure x. But I'll go quickly through it because I will enter them later on in more detail. No? Well, this is the probability distribution as a function of time. This for the number of photons, 2, 4. And this is the moment of the occultation. And here you have one, here is with 1 microsecond resolution, but like here. And here you have basically the intensity, the intensity curve, which the occultation lasts, let's say, 10 seconds, more or less 10 seconds. And the intensity decreases by a factor of 5, about the factor of 5. And here you have the distribution. You have the distribution, the probability distribution of the number of photons in a microsecond, always in a microsecond. And this is the probability of 1, 2, 3, 4 photons in a microsecond before the occultation and during the occultation. You may see that there is that the probabilities decrease, the intensity decreased by a factor of 5, but the probability of the large number of photons decrease very 2 orders of magnitude in some cases. No, in this case, for example. No, and well, a very simple model has been used to infer the angular side, of Betelgeuse. Well, this is a trivial expression. The E drop that it is it depends on what is the portion, the portion, the cover, the portion of the stellar, of the star covered by the asteroid. No? And it is a relationship between the angular side. And since the angular side of the asteroid, which is it is 1.8 the astronomical units away, and have some 66 kilometers in the mean radius or diameter, the mean diameter. Sorry. The total angular side is 50 microsecond, micro-arc second, 50 micro-arc second. So we see that if we use this expression, we obtain this. But you may know that to do this inference, that means that in the central moment of the occultation, the asteroid is wholly inside the angular side of the asteroid is completely with that of the star, and which is not the case. So in principle, there are two things: the limb darkening effect that have not been taken into account that will increase this number. But I think that is more important this fact, and probably the angular size of the star is closer to 50 or even under 50. No? That's my opinion. But no exhaustive analysis have been carried out because it was just a demonstration. Yeah. So, well, now I come to explain my part, my contribution, where here, as I said before, we will we will discuss very general concept in the area of statistics, especially in the area of photon statistics. First, very general consideration. What is a process? A random Poissonian process. A random Poissonian process is a process whereby you want to create a distribution. You have the galaxy, for example, and you want to mimic, to make copies of to make realization of the distribution. One way of doing it sequentially. You start placing point at random. If you place point at random with a uniform probability, that is the simple Poissonian. No novelty about that. The distribution, the probability distribution of having n in a given volume is perfectly given by Poisson. But for example, if you are considering you want to reproduce the large scale structure of the universe, you can do it most of it. You can do most of it with the Poissonian process, but not the uniform random Poissonian processing. You have a field of the probability density, and then you play the point. When the probability density is high, you play the point here with more probability than here. Okay, this is very interesting because many models can be many distribution can be modeled by non-uniform random Poissonian process. The large scale structure of the universe. For example, when I was carrying out my thesis, I did work in the probability of voids and another structure. And in a scale of, let's say, 10 megaparsec or so, and above, large-scale structure is perfectly described by the non-uniform random Poissonian process. The field is given by the field of perturbation, the initial one that grows with gravity, that there is a biasing. It is not the field of mass, but the field of mass gives you transforming into a field of probability density. Okay. And for void, in any scale larger than 10 megaparsec or so, work perfectly. But I wanted to see how important was the non-Poissonianity, because in a smaller scale, it cannot be a Poissonian process. Why? Because when you place a galaxy here, you cannot place a galaxy on top of it. In fact, you cannot place one because of many considerations, like tidal field, very close to it. And so the principle of a random Poissonian process, you have the underlying field that dictates how you place it. But when you place a point here, you do not modify the probability of putting another place. Everything is controlled by the underlying field. Okay. And then I consider a model and say, imagine a model in which when you place a point at one place, the probability of initially you have the probability detected by the field. It may be uniform, it may be non-uniform. But when you place the point, the probability is given by the field, but also in the neighborhood of the point is modified with certain function given by the physics. Well, I consider that model in very general terms, and well, when you consider this possibility that the point modify the probability of subsequent points, you leave the region of Poissonianity. But as I say here, there are as many types of distribution, non-Poissonian, as way of modifying the probability in which a point can. It is very open. But the important one, the interesting one, is the one that I call, I say, let's see one of them, very general. There are many, like you have Gaussian distribution and non-Gaussian distribution. Gaussian distribution is just one. Non-Gaussian, it may be non-Gaussian in 100,000 ways. Here is the same, but there is one very general, which is processor non-Poissonian in a non-Poissonian random field process. There is there is an underlying field that may be homogeneous or not for placing the point, but the presence of a point imply the modification of the probability with certain function. And the specificity of this particular, but very general, non-Poissonian process is that the contribution of the different points combine linearly. What does it mean? That if when I place a point here, in the neighborhood of it, the probability of coming another point, it would be modified. If there are two, it will modify, it could be additive. Okay? So it would be proportional to the number of points, the modification to the number of points in this region. Well, then I showed that I obtained this distribution here. I didn't know at that time that it was called negative binomial. I obtained this distribution. This is in 3 dimensions. So I put lambda time delta V is the volume in which we are looking for this endpoint. And this is the mean number to be expected there. No? And but we have we showed before, we have this extra parameter, and that of course when theta goes to 0, this goes to Poisson again. But the important thing is that this theta parameter, because this distribution was known. I didn't know that it was known, but it was known, and it's called the negative binomial, and people use it with certain parameters. But what haven't been done before is to show how this parameter is related to the underlying physics. While in my work, I show how this theta parameter is modified by the physics, or by the way in which a point modifies the probability of subsequent point. Applying this to the arrival of a photon, which is just one of these distributions, but in one dimension, just time. Well, I refer to this work precisely, the Prada et al. 2024. And as I said before, the arrival of the photon in themselves is independent. So we have in principle, we have a uniform, in principle, we have a uniform Poissonian process for the photon themselves. Okay, uniform is during the time you are observing, the rate doesn't change, of course. So the arrival that I say, this is not exactly true, but in this context, it's almost true. The photons in themselves are almost independent, independent particles. No, but the detection, the detection of the event are not independent. There are just two effects that I mentioned earlier, and I comment here in more detail. Optical crosstalk, the detection in one element of the array have a small probability of activating an element, a close element, an adjacent element, generating a spurious detection. If during a microsecond, which is the time we're using to obtain the probability distribution, an element is activated, it cannot be activated one more during that microsecond. So we have reduced the number of possibilities of detecting the photon very, very slightly, because the mean number the effective number of pixels is given exactly by the expression. I don't remember how they derived it, but it is the tag. This is the n sub y is the number of photons that fall into the pixel, the white pixel. And this determines the effective number of pixels that are being used. And the non-Poissonianity, the effect of non-Poissonianity is this. Theta time lambda time delta t, lambda time delta t is the mean number of events in a microsecond. Well, if t is delta t is a microsecond. And it's related to the crosstalk and to the number of effective pixels used, and lambda, time 1 microsecond. And well, this can be computed. This is like 70H or so, no? And so we can infer, as I will show immediately, we can infer with great precision this parameter, x, which is the only unknown here. This we know, and x or theta are the unknown parameter. Here I give the comparison between this is the point and the actual measurement, no? And you see the discontinuous line is the Poisson. This is the negative phenomenon. You see that it fits perfectly. And there is a small, if one look up to here, look at here, for example, is the probability of tangent the minus T. If one look here, one wouldn't say that there is non-Poissonanity. There is no Poissonanity. That the process is purely Poissonian. But these small discrepancies, very statistically significant, allow us to measure this with great precision. Just to finish, for example, is I repeat here that the effects are very small within 1 microsecond, but if one goes to the tail of the distribution for n, 3 photon, 4 or 5 within a microsecond, when the mean is 0.15, there are some discrepancies. If you compute the chi square for Poisson, is 2000. If you compute it for binomial negative, is 2 or so, 2 or something like 2. Carrying out the best fit, we obtain theta, and immediately we obtain the value of x, which is a 1%, approximately 1%, but with a very small error. And this is completely in agreement. It's in agreement with what has been found in the laboratory. But in the laboratory, you have to do it for every single element. Every single unit is very complicated, and then you have to. They differ, and then you have to give them the weight that they have in the actual observation. And but if this were done, carried out, and statistical significance were to be found, it means that time effect, because all the treatment is exact. So any statistically significant discrepancy would mean that there is some effect that we have missed. Well, we studied also the distribution of the time of arrival, of the time between one event and the next event. No? The interval between arrival, and with the negative binomial distribution, this is, I'm finishing now. With the negative binomial distribution, this is the distribution, but it's there is barely no difference with Poisson. It's practically because theta is very small. There is almost no difference. But here we shall see in the next. Here is the you can see the result of the comparison between the observation and the prediction with negative binomial distribution Poisson. practically here you don't see the difference. Here with the residual, practically no difference. But there is an important thing to be taken into account in this case, because if you were to use Poisson, simply Poisson, you will not find agreement. Here, in this case, for the interarrival, what is important is that the process is almost Poissonian, but not uniform, because during this 50 seconds of this observation, with 5.6 or so million events, the atmosphere, the condition of the atmosphere change a little bit. So if you compute the variance and the number count is much larger than the Poissonian. It means, but not because of non-Poissonian effect, but simply because the rate of count here is different than the rate of count here. So you use Poisson, but you have to take the Poisson with the local count rate and then average overall instead of what people do, the average the rate and then introduce it into the Poisson. No, you have to put into the Poisson formula the local rate and then average overall time. So this is what we have to learn from this is that everybody working with when people want to push the statistic, the conclusion of the statistical analysis, you must be very careful with photon statistics, for example, because you may have an effect simply non-Poissonianity due to the change in the condition. Very small changes in the condition increase the variance. And increase the variance, and here we see it through the interarrival probability distribution. So let's see, in conclusion, so this, now what is important now is that we have to take this into account, that the lambda is not uniform, and we have to obtain the correct distribution. This is the distribution of y, being that the interval between the event is y times delta t, which is a microsecond. And well, to obtain, as I said, to obtain the correct distribution, we have to average this distribution over or Poisson, which is practically the same. But we have to average it over all possible values of the local counting rate. And when one does this, the correspondence with the observation is very good, except for the first point. Except for the first point. This is here is something, well, that I cannot explain here, but it is irrelevant. But the important thing is that there is a 5% excess. And this is related by after-pull effect, which is quite important. After-pull effect means that when you produce an avalanche in a unit, the avalanche lasts some time, during some time. It is supposed that after the resolution time, or a few times the resolution, which is 3 nanoseconds, I will say here, although we work in 1 microsecond, but the resolution, the intrinsic resolution, it should be relevant. But here we have found that after a microsecond, there is still a non-negligible probability that the element is still on avalanche. Okay, that is the interpretation that we have done of this. And well, one can do a very simple model. One can carry a very simple model with a P0 is the probability that an element that is in avalanche would be still in avalanche 1 microsecond after. And it's like a 6 per thousand, so it's pretty small. No? And to point out that our data do not provide evidence of the existence of the dead time, so that the system can deal with any amount of event. Following. What happened? El siguiente. No me sale el okay. Well, here we go to the conclusion. This study demonstrates the potential of the two-dimensional SPAD, one-dimensional have already been used in astronomy, apparently for the first time, and set a new standard for observing very rapid phenomena, the transient celestial event, because of the time resolution that can reach and go below a nanosecond. We have confirmed that this effect, that the distribution depart from Poissonianity merely due to the detection effect. And we have inferred that the probability of the event avalanches has a very long tail, because the technician determine the distribution of the time, determine the time of the avalanche, but they characterize it by a mean and RMS or whatever is not enough, because it characterizes the main portion of the distribution, but have a very, very long tail, which it would be very important in designing this instrument, in designing instrument for the LPY. No? And I mentioned here, stress here, these findings are in agreement with photons arriving independently, as people expect. This is not true in general, but in this case, it is true. In general, they obey a binomial negative distribution also. And to finish, just remark that just these two remarks, that the characterization of the Pax signal statistic plays a crucial role in designing the SPAC detector specification with nanosecond time resolution for the alarming interferometer, in particular the after pulse effect, because we have to say to the engineer that they have to characterize the distribution very carefully. Because this, you see, in 1 microsecond, still there is a probability of the avalanche continuing. But then we will work with 1 nanosecond. It would be much more important. So this is one of the conclusions. We are expecting first interferometer result. Well, there is a proof of concept that in the coming month, for the next fall, I think, with an SPAD camera, and with this proof of concept would be already not just for the SPAD. This talk is just for the SPAD, but for the context, this is a proof of concept of interferometry, because are using a single telescope, but are using different portions of the surface of the telescope. To obtain do interferometry between them. It's just proof of concept. It will not achieve a higher resolution than the telescope itself. With interferometry, it can be done. You could obtain more resolution than with the full disk. But here no. As I say, it's just a proof of concept. And also remark that I forgot to say that I mentioned that the SPAD, one of the limitations, very severe limitation, is the small coverage. And 3.5%. And 70, something like 70% if a photon fall in the sensitive area, still have only probability of 0.7. But this is not much, but 3.5% of coverage. People have done cameras with over 90% coverage. But look, you remember the arrays, yeah? And the microelectronic developed by the unit of microelectronic of the Institute of Microelectronics of the University of Seville. there is all this macroelectronic that limit because it's surrounding the unit. The macroelectronic is surrounding the unit. And there is the next stage is when you put the electronic backstage. But this is a major step, and they will try to do that in the future. But in the more near the more near future, the development is just to insert micro lenses, to try to insert micro lenses, and well, there are other options that I will not mention here. I think it's enough what I wanted to say.
Okay, thank you, Juan, for the talk. Any questions for Juan?
Thank you, Juan. A very interesting talk. Let me understand, in your picture during the experiment, during the photometric experiment, in each individual pixel, in each microsecond, how many photons you received? And what is the...
0.15. 0.15.
0. Per microsecond.
Empty. There are no photons in most of them.
Okay.
Only each 8 or 7.
So basically you receive 1 photon per pixel per microsecond, or less.
Much less.
Less. And the avalanche effect, the tail, the tail that you were mentioning would be at the level of 1%. For less than 1%. Okay. Okay. Thank you. So I suppose that in the future, the SPADs will be coupled with integrated photonics in order to send them directly, the photons through a kind of fibers that are integrated in chips. I think that's the way forward.
In this low coverage array, there is a 1% crosstalk. You have to, if you put them very close together, you have to be much more careful. I don't know. I know that there are cameras, cameras, for example, that operate with 90% or so coverage. I don't know what the crosstalk is, because probably the crosstalk for Moxie is 5% or so, probably is not important. In here, it's important. It's important in particular because I didn't talk about this here, but when you make interferometry, you have to imagine that what you receive here is an independent photon. And here, independent photon. Why should there be a correlation between them? In fact, when the people, the first Hamburg, Brown, and Twist proposed this in the 50s, what is it that? Yeah, it's nonsense. It's nonsense. And you have a shower of photon here, a shower of photon here. There's no correlation. There is no correlation that has to do with the wave matching, because usually we're working when we look at the sun. We are in the visible. We are in the BN regime of the plan distribution. We are in this region, BN regime. That means occupation number very small. And that means that photons can independently of one another. Simultaneous, very small proportions to that come in bunch of two. Very small proportions. When you have in radio, all can be occupation huge, occupation number. No? By the optical, the photon of people working in a similar like that. The photon is a shower of independent things. No? But we are going to by the interferometry, in the visible, it just takes this very small departure of in this one you obtain basically the photonic, remove all the effect of the detector. This kind of that. Here, when we discuss all that, photon count absolutely independent. We cannot do interferometry with that, because here in the photon in the telescope and in this telescope are independent. Everyone here is independent of the next one, and more independent are the photon here and the photon here. But we have to take advantage of this, because a few of them coming back, but still there is an exact equation here. The variant, if you compute the variant, you remove all the fact the variant is not the Poissonian. It's not proportional to, it's not n, the number of photons that you are repeating. The variant of the number of photons counted at a given time is not just the number of counted, the variant, not all the square, the variant. And it's larger, it's a little bit larger. A little bit maybe 1%. 1% indivisible, 1% larger. And when you do the thing correctly, you would detect this in this telescope. And it is part this effect of Poissonianity. Here, that is correlated with that here. Because the wave nature of the photon only manifests when the photons do not come one by one, but come in bunches. When the base number is not very small, so that there is some probability that come in bunches, few of them come in bunches of 2, very few of them come in bunches of 3, and so that will mostly very small proportion that can do. Let's see, 20,000 folk and a little bit more than 5,000. And so it is the essence of the interferometry for the situation on the wave nature of the photon. The wave nature of the photon is related to the fact that the photon is not photon. That is one of the facts that I mentioned, that one photon has a larger probability of having one close particle, impacting the same step, the same both cell. And it is a very small thing that when you count the million of photons, you end up finding the excess of knowledge here, the non-Poissonianity of the photon themselves. In this cell, the excess on this and this excess is correlated. And the correlation, of course, falls with the distance, and when it falls a certain amount, it's related to the size, the angular size of the cell. That is another talk, but I guess I wanted to say things I mentioned that in this talk, the photons are not correlated. So in fact, they are, they follow the phenomenon distribution, but it's very small amount of non-Poissonianity in the visible, but it's just precisely this non-Poissonianity that is correlated between the telescope and allows the intensity interference. So that we correlate the fluctuation here with the fluctuation here. In each one of them, there is the fluctuation in very small excess with respect to the sun. But this very small excess is correlated here and here. But the end we did the distance, that the correlation is it, the larger the cycle of the solid, the smaller the distance. Go for an even number side, go and separate the telescope beyond certain distance, there is a correlation here.
Okay, any other questions for Juan? We have time for another. Nope. Okay, so thank you again, Juan, for the nice talk. And thank you all for coming, also for the ones in Zoom. And here we close the session of today. Thank you.